So this question is quite a bit of work. It says, how much energy does it take to heat 180 grams of water from 35 degrees C to 115 degrees C? And it gives us some constants below. So it gives us the specific heat capacity of ice, water, and steam, and it gives us the enthalpy of fusion and enthalpy of vaporization. It assumes that we know the melting and boiling point of water. So if we look here at a phase change diagram, which is basically what we're doing here, okay, we have heat being added in this direction. And over here, we have the temperature in Celsius. So we're adding kilojoules of heat in this direction, and we're going to have a temperature. Now we need to write the milestones. All right, the milestones are the temperatures you're given in any phase changes. In this case, we're only going to go through one phase change because we're starting with liquid water and we're heating it up to form steam. We don't have ice in this case. So we can start at the bottom with 35. We could put 100, all right, that's kind of hard to see, so I'm going to put this degree C over here, and 115. It's not perfectly to scale. Okay, so basically, we're going to heat water from 35 to 100, and as we add heat, the temperature will change. This is the same as putting water at 35, which is slightly higher than room temperature, and boiling it on a stove. Then something's going to happen. When we hit 100 degrees, we're going to add a bunch of heat, and the temperature is not going to change. Note that this is not proportional. If this was proportional, I need to draw this line way over to here. Okay, so we're adding heat and we're vaporizing the water. Specifically, we're turning the water from a liquid to water as a gas. Where then, once we have the steam, we can add heat and the temperature will rise again. So we have the two sloped ones. This has a slope of 0, but the two non-zero sloped ones, and then we have the part where we're adding heat, but the temperature is not changing because we're separating the molecules. We're going from a liquid to a gas. We're going through a phase change, which is why this is a phase change diagram. These two sections are described by the equation that you learned a long time ago, which is Q equals M, mass, C sub S, delta T, where M is the mass in grams, C sub S is the specific heat capacity given here in joules per gram degree C, and delta T is the change in temperature. This section, this flat section, is what was in the previous two questions, or you could think of it as Q equals N is the moles, times in this case the enthalpy of vaporization, because we're boiling the water. It would be the enthalpy of fusion if we were melting the water. But here we're boiling the water. So these are the two equations that we're going to need. Unfortunately, because the specific heats are different for steam and for water, we actually need to treat these two sections separately. So we have actually 3 calculations that we need to do in order to solve this problem. So the first calculation we need to do is from a liquid at 35 to a liquid at 100. And the equation you want to do when you're changing the temperature is Q equals M C sub S delta T. So, you don't need that equals. Q, the amount of heat, is the mass, 180 grams, times the specific heat capacity of liquid water, 4.18 joules per gram degree C, because water is a liquid between 35 and 100, times the change in temperature, so 100 minus 35, which is 65 degrees C. When you do that math, you find that the amount of heat added here is 48,900 joules to 3 sig figs. Since I know that the part 2 is going to kick out in kilojoules, I'm going to go ahead and convert this to kilojoules divided by 1,000, which is 48.9 kilojoules. All right, now let's look, oh, you can't see that. Let's look at section 2. Section 2 is from a liquid at 100 degrees C to a gas at 100 degrees C. Here, Q equals N times the enthalpy of vaporization, which is given right here. But we need to find moles. So we need to take our 180 grams of water times 1 mole of water per 18.02 grams of water, which is going to be 9.99 moles of water. So we take the 180, we divide by 18.02, and it's almost 10. So now we can plug in. Q equals 9.99 moles times 40.7 kilojoules per mole. And when you do that, you get 407 kilojoules to 3 sig figs. Note that this is, I don't know, 9 times as much as this one, okay, approximately. So 8 to 9 times as much as this one. So it's way more energy. Said another way, the distance here, this should be 8 or 9 times longer. It should be way over here, all right, if we were drawing it to scale. So it takes a massive amount of energy. Why does it take so much energy to do this? Because you're separating the water molecules when they're nice and close together in the liquid phase to where they're essentially completely separated in the gas phase. That takes a lot of energy because water has strong intermolecular forces. Section 3. Section 3 is now from a gas at 100 to a gas at 115. Note that when you have a change in temperature, you use the equation with the change in temperature in it. All right, that's just kind of a way to remember if you're not sure which one to use. So here Q equals M C sub S delta T. All right, the mass, it's still a 180 gram sample. The specific heat capacity of steam is different than water, which is why you can't combine these two steps to a whole total temperature change. So it's 2.01 joules per gram degree C. And the change in temperature here is 100 to 115, which is 15 degrees C. When you do that math, you get 5430 joules to 3 sig figs, or 5.43 kilojoules. But remember, it takes the total amount of energy. So Q equals 48.9 kilojoules plus 407 kilojoules plus 5.43 kilojoules, or the total amount of energy is 461 kilojoules. So these phase change diagrams, are kind of a pain in the neck. And here we only went through one phase change. If you went through two, or if you started this at, say, minus 35, and you both melted it and you boiled it, then you'd actually have to have 5 steps. All right, so it would add 2 steps if you were going to do that. So these questions are quite a lot of work, and it's a good idea to practice 1 or 2 of these to make sure you've got it.